Welcome back to Unit 1, Chapter 4, Quadratics. We are going to shift gears from factoring today a little bit, continue with quadratics though, and we're going to start section 4.5. This part of 4.5, what I want to focus on is being able to simplify radical expressions. Break down square roots, basically. We're going to simplify them. It's going to be a lot like reducing fractions. That's what simplifying radical expressions can be compared to. It's a similar process. But by the end of this lesson, you should be pretty comfortable with simplifying radical expressions. Okay, a radical expression is something with a square root in it. Okay? In order to break down and simplify radical expressions, we need to be able to list perfect squares and use those. Listing perfect squares is the easiest thing. You should all want me to give you a test on listing the first 10 perfect squares, 20 perfect squares, because it's really easy. This is how you have to do. I know you all can count by ones. So you start at 1, 1, 2, 3, 4, 5, 6, 7, 8. We'll go up to 10 to start. You can make this list go as long as you want. Okay? But if you want to find a list of the first 10 perfect squares, you square each of the first 10 counting numbers, first 10 positive integers. So the first perfect square is 1. The second perfect square is 4. The third perfect square is 3 squared, which is 9. 4 squared is 16. That's the fourth perfect square. 5 squared is 25. 6 squared is 36. So this is the easy way to list perfect squares. And no, I am not going to provide you with this list for a test or a quiz. This is something that I feel that everybody in this room, you may not be able to multiply in your head, but you all have access to a graphing calculator when you're in my room. And many of you outside of the room, or a calculator in general, and you can square too. You can write this list and square each of these numbers, and then next to them, write the output. And those are the perfect squares you're going to be working with. Why are they called perfect squares? Well, because for instance with 4, the square root of 4 is 2. That's why 4 is a perfect square. Why is 16 a perfect square? The square root of 16 is 4. So these are the perfect square numbers. How come 2 isn't a perfect square? How come 3 isn't a perfect square? Well, what do you get when you square root 2? You go to your calculator. If I squared a second x squared, if you saw me do that, and I square root 2, I get 1.444. 414, excuse me. So the square root of 2 comes out to be this number that really is not nice. It's called an irrational number. There's no pattern to it. It doesn't repeat. You can't write it as a fraction. In fact, if you go in your calculator and you hit math fraction thinking I'll get around this, it gives you the same thing. If you hit math fraction and it won't reduce, 99 times out of 100, that means it's an irrational number. There are some times where there's really big fractions that your calculator can't handle. But we're not going to run into those too often. So, that's the difference. What makes something a perfect square is something that when you square root it, you get a nice number. How can we list them all out in order? That's how. Make a list. Now, if I needed a bigger perfect square, I just keep going. 11 squared, 12 squared, 13 squared, 14 squared. You can go on and on, obviously, forever and ever and ever. Okay, but that's what we mean by perfect squares. What is a perfect square? What is not a perfect square? Notice the numbers between 1 and 4, 2 and 3, they are not perfect squares. 5, 6, 7, 8, not perfect squares. 10, 11, 12, 13, 14, 15, not perfect squares. Okay? So keep that in mind. Oops. Okay. Properties of square roots. Product property and the quotient property. So here's some notes to make sure you're copying down, and I know you copy down all the examples that have these properties in there as well. The product property says if we have the square root of something being multiplied, it could be 2 things, 3 things, 4 things. In this case, I just wrote 2, but it could be A times B times C. That would work as well. But something being multiplied, I can separate that into the square root of A times the square root of B. The converse of that is also true. If I have 2 things separately being square rooted, I can multiply them together under 1. If they're being multiplied separately and being square rooted, I can multiply them as one product under one square root. So that's a product property. We're going to use both versions of it. So have both down. Or if you just write one down, doesn't matter. You can go left to right or right to left with the properties. Quotient property, what's a quotient? Product multiply, quotient means fraction or divide. So quotient property says if I have A divided by B, I can square root those individually. Or if they're square rooted individually, I can square root them together as one. So those are the properties. If you need to get all that, go back and calculate them down, pause it. Remember, that is your right. You are in charge of how fast or slow you cover this information. Okay, so let's do some properties. Some examples, I should say. We are going to simplify each radical. What does that mean? So it's like reducing fractions. Okay? And it is. Simplifying radicals means I want to make what's inside of the square root as small as possible. And you're saying, I don't get it, what you're saying right now. That's fine, you may not. Okay? But you will by the end of this slide, I hope. Okay, so if I want to simplify the square root of 24, the best thing that could happen to me is I go to my calculator, I hit second x squared, square root 24, I cross my fingers, pour salt on my shoulder, I don't know, whatever it is for good luck else you would do, and I hope that I get a nice number, but when I hit enter, I don't. When I say simplify, this is not what I want. Okay? Simplifying the square root of 24, this is not simplified. That is not simplified. That is finding the approximation. This is the decimal approximation, which you may use if you're an engineer. You may use that to get a length or whatever you're using to build something. But right now we're mathematicians and we're trying to simplify. And that's not simplifying. Okay, that's different. So if I'm asking you to simplify a radical, here's what you need to do. The first thing is on your paper somewhere is the list of perfect squares. So you're going to recreate this list on your own paper because I'm going to show you how you're going to use it. We just did it previously, so you may have it written down already. I'm writing it down now. It's a reference for you. How far we need to make this. We'll go down to 10 again, I guess, just because we did before. So let's fill this in here. 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. Okay, so perfect square. We already confirmed that square rooting 24 not going to work on our calculator. Okay, so what we did learn, though, or can see, is that on this list, 24 would be right about here. It'd be between 16 and 25. So what we're going to do is we're going to say, okay, right here at 24, we're going to work our way back upwards. 16 divide 24 evenly, there's 9 divide evenly, 4, 1. Why am I working backwards up the list? I want the biggest factor that is also a perfect square that will divide 24. When I say, what is a perfect square that divides 24? Somebody's going to yell out 12. And I'm going to say, no. 12 is a factor of 24. But 12 is not a perfect square. It's not on our list. It goes from 9 to 16. 12 is not a perfect square. So it doesn't help us. And I want the biggest one. Okay? Because it makes you just do this one step. If you work your way from the top down, you may find a perfect square that divides it. It may not be the biggest one, and then you have to keep going. If you work your way backwards up the list, you find the biggest one right off the bat. It just makes your life a lot easier. Trust me on this. Okay? So 24. And in my calculator, I'd say 16 is the first one smaller than 24. 24 divided by 16, I divide it. If I get an integer, I'm in business. So no decimals. I enter 1.5. That's a decimal, not going to work. Well, 9 divide 24. Some of you may be able to do this in your head. Others may not. So 24 divided by 9, that doesn't work. hopefully 4 works. If 4 doesn't work, then it already is simplified. That'd be the best thing, right? It already is simplified. We don't have to do anything. Let's divide 24 by 4. Uh-oh, that's an integer. It works. 24 divided by 4. We've proven that 4, which is a perfect square, divides 24. So we're going to use the product property, and we're going to split this. We're going to rewrite 24 as 4 times 6, right? That's what we just proved. 4 divides 24. So we're going to split this up in the square root of 4 times the square root of 6. A lot of times we just go straight from this step to this step. But I'm showing you why you can do that. Zero product property. What is the square root of 4? The square root of 4 is 2. We have simplified it. 6, you can always check in case you didn't get the smallest one, but 6 would be between 4 and 9. 4 does not divide 6. 1 does, but that doesn't help us break it down anymore. So if the only perfect square that divides it is 1, then it's simplified, that square root part. So we have now simplified the square root of 24 into 2 times the square root of 6. And you're thinking, Mr. Kuhn, that does not look more simplified to me. I have a number outside and a number inside. I agree. Okay, this is not, if you want to say the most important things ever to do in math, simplifying square roots, I'm going to be honest with you, probably does not make the top 100 list. But it's something that we are going to be tested on in the ACT, something that you may see done in, just in this class on the tests and quizzes, but most importantly on standardized tests. So it's something we have to know how to do. Let's check our answer to see if we got it right. And this is going to be something else I can help. How can we check our answer? Well, square root of 24, we already know that equals 4.89897, et cetera, et cetera, et cetera, right? When we type in 2 square roots of 6 on our calculator, we better get the same answer. So 2 times the square root of 6, what do we get? We get the same exact answer. We get the same decimal value. They're the same. Okay? So this and this are the same. If we get the same decimal, then they're equivalent, and we've done something correctly. Sometimes people get in a rush and they mess this up, and instead of writing, they write, I don't know, they get jumbled up. They write 6 square roots of 2. How can we prove 6 square roots of 2 is not the answer? When I type in 6 square roots of 2 in my calculator, I don't get the same decimal. Okay? So that's how we can show that something is right or wrong. If we did it wrong, we'll go back and look and say, okay, what did I do incorrectly when I was going through the problem? But that's how you check it. If you have a multiple choice problem on the test, you're in luck because it's really easy for you right there. You can just match up the decimals. Okay? Let's try another one. This is one now where I want you on your honor. I want you to practice this first. You try it, pause it, and then come back and check your answer with me when you're done. Okay? So I'll give you a second. Go ahead and do that one. Hit pause, and come back when you're done. Okay. 27, you probably tried to square root it in your calculator away, didn't get a number, right? You got a decimal. So what do we get when we square root 27? When we square root 27, we get 5.19. Okay. So it doesn't work. But you did notice, just like we do with 24, let's erase the 24 over here because you already got that down. 27 would slide in between 25 and 36. That's where 27 would fit. So we're going to work our way backwards from 25 back and see if we can get a number that divides 27. Okay? Will 25 divide 27? Nope. Will 16 divide 27? Nope. Hopefully you did this on your calculator like I did last time, systematically dividing them. 27 does divide by 9. What's 27 divided by 9? It's 3. So really this is the square root of 9 times 3, or the square root of 9 times the square root of 3, which is 3 square roots of 3. If we did it correctly, and we plug 3 square roots of 3 in our calculator, we should get the same decimal. In fact, we do. So it shows us that we did something correct. Now maybe it can be simplified further. If you're worried about that, take that square root part. 3 is between 1 and 4. The only perfect square that will divide 3 is 1. We're good to go. Okay? Let's see here. Same thing, you try this one on your own. Square root of 96. Hit pause, go back, reference that list of perfect squares. This is why you want to have that list of perfect squares on your notes, and when you're doing problems, just write it out on your homework sheet. Or in class, write it right on that piece of paper you're doing your in-class assignment on. You're going to be helped out quite a lot. So hit pause, and then come back and see me when you're done. Okay, 96. Where's 96 fit on the list? It's almost all the way at the bottom of this list, but I mean, there's lots of perfect squares past 100. So we work our way backwards from 96. 81 does not divide 96. 64 does not. 49 does not. 36 does not. What does divide it? 16 does. So 16 times 6 is 69. So this is the square root of 16 times the square root of 6. Or 4 square roots of 6. Check it on your calculator. Remember, you always want to do that. This is the easy ones to check. Guys, it's not going to get any easier than that. And that hit 4 square roots of 6. They're the exact same. We got a winner. Okay? Hopefully you're saying, man, this isn't so bad. One more. What if we have something like this? What do we do? Well, remember the zero product property, not zero product, the product property for radical equations or expressions it says that we can either separate them or we can multiply them together. These are each being square rooted separately, but multiplied together. So we can rewrite this as 10 times 15. Why would we want to do that? Well, we get one number, the square root of 150. So now we just have to simplify the square root of 150. To do that, we might have to extend our list a bit, right? 11 squared is 121. 12 squared is 144. 13 squared is 169. So that's as far as we have to go because it's 150. So if we think 150 would fit in right about here, let's work our way backwards. Does 144 divide 150? Nope. Does 121 divide 150? Nope. Does 100? 81 doesn't. 64 doesn't. 49 it does not. 36 does not. But 25 does. 25 divides 100. In fact, 25 goes into 100 6 times. So the square root of 25 times the square root of 6. The square root of 25 is 5. The square root of 6 does not break down, so we get 5 square roots of 6. Calculator time. Square root of 150 is that number. This number. And 5 times the square root of 6 is the same thing. Okay, so this is how you simplify radicals using the product property. Rewind and go back if you need any more. When you go anymore. Okay. Here is a key fact as we go through this simplifying process. You can never, ever, ever, and I don't know why I didn't make up the rule, so don't yell at me. Don't get angry with me. It's not my rule. This is the rule of math. So I'm just following the rules and letting you know how we have to do it. But you can never leave a square root in the denominator of a fraction. Okay? You can never leave a square root in the denominator. You have to get rid of it. That doesn't mean erase it, cross it off, pretend like it's not there. We have to legally, mathematically redo or get rid of square root. So, a quick review from Algebra 1. Okay? Well, actually, you can review just what we learned here, too. Square root of 3 halves. What's the square root of 3 over the square root of 2? That's not simplified. Okay? Because there's a square root in the denominator. We cannot have a square root in the denominator. It would be nice if it were like this. It was a square root of 3 over 4. Square root of 3 over 2. Now that's simplified. This is not. Okay? Because the square root of 2 is in the denominator. Okay? So, what do we do? What do we do? We have to rationalize the denominator. Now, I know rational If you're a rational person, you think things through, you have reasons, you support your argument. So we're not going to rationalize the denominator by talking to it and saying you really shouldn't be a square root and giving it reasons why it can't. That doesn't make any sense, does it? So that was my attempt at a rationalizing joke. Okay? Not very good, but just seeing if you're awake out there. But rationalizing the denominator, that means just eliminating the radical sign from the denominator. And this is how we do it. So if we look back at this example up here, the square root of 3 over 2, we split it up into square root of 3 over the square root of 2. Here's how you rationalize the denominator. We rationalize it by, let's just get rid of this screen altogether here, don't need it. We rationalize it by taking whatever is in the denominator, whatever square root's in the denominator, I don't care what's in the square root of the numerator, and we're going to multiply the top and the bottom by that square root. Why can I do that? Why does that work? Why is that legal? Before I even move on, what is the square root of 2 over the square root of 2? It's 1. So I'm really multiplying that by 1. I just wrote 1 in a funny way. But when you multiply by something by 1, it doesn't change its value. A billion multiplied by 1 is a billion. 10 multiplied by 1 is 10. Even if I rewrite it in a funny fraction like this. This is just the loophole we have here by rewriting 1 as the square root of 2 over the square root of 2. It's a loophole that lets us rationalize the denominator. You're saying, well, how so? What's going to happen? Well, square root of 3 times square root of 2, that's just square root of 6. The square root of 2 times the square root of 2 is the square root of 4. And why is that interesting? What is the square root of 4? The square root of 4 is 2. So the square root of 6 over 2 is the simplified version of the square root of 3 over 2 as one fraction. Okay, and how is it done? By rationalizing the denominator. Whatever is in that denominator, you multiply the top and the bottom by that square root. It's legal because it's really just 1. That's why rationalizing the denominator works. Okay, it's our loophole around doing it. Remember, we always want to check and make sure we did things correctly, or that it worked out what we did. So the square root of 3 divided by 2, what do we get for that? We get 1.22. Okie dokie. And then we want to do the square root of 6. I'm going to do my fancy fraction app just to remind you that we can do that. Square root of 6 over 2. I get the same thing. Same thing. So we did something correct. Okay? One more for you guys to try. One more for you guys to try. The square root of 2 over 15. Hit pause. You try and do it. This is using, obviously, the quotient rule to separate it and then rationalizing the denominator. When you're ready, go ahead and come back and finish up and we'll check it. Okay, well, hopefully you at least started off with this by splitting it into 2 different radical signs for the numerator and denominator. Square root of 15, put that in your calculator. It doesn't work out too well. So, what do? We rationalize the denominator. What's in the denominator? Remember, the denominator is, we talked about this before, but the denominator is the bottom of the fraction. Okay, hopefully you remember that term, but it's the bottom of the fraction. What's the top of the fraction? The numerator. So square root of 2 is the numerator, square root of 15 is the denominator. We should discuss that earlier, but I'm assuming we all remember that from our middle school days. So I multiply by square root of 15 over square root of 15. Remember, that really is just 1. When I divide those, it's going to be 1. So we get 2 times 15, which is 30, the square root of 30, over the square root of 225. The square root of 225, put that in your calculator. Or continue your list out. What is the square root of 225? It's 15. Right? So the square root of 30 over 15. The only thing I would look and say, can 30 be broken down? Does 30 have a perfect square that divides it? Oops, in my list of perfect squares, I forgot it's on my last page. So real quick, just to review, because you always should think about that. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. And that's 36, 25, 16, 9, 4, 1. I don't believe that 25 will divide it, 16 won't, 9 won't. 4, will 4 divide 30? I don't think so. Let's check. 30 divided by 4. So I know some people out there doubting me. Nope, it won't. 7.5. I was right. So nothing will divide it. So it's simplified. If no perfect squares will divide it, it's simplified. That's our answer. Of course, the final check would be plugging the original problem in. 2/15 square rooted. And then plugging in alpha y equals square root of 30 over 15, and get the same answer. Okay? So, rationalizing is just another way of saying simplifying. It's getting the square root out of the bottom. I don't know why. To mathematicians all around the world, having a square root in the denominator of a fraction is like nails to a chalkboard. Okay? So, one more. Rationalize the denominator using conjugates. So if we ever have a problem like this is more of an advanced type problem, and we're going to get into stuff using conjugates a little bit later in the year. So we might as well cover what a conjugate is. A conjugate, what if our square root in the denominator has something added or subtracted to or from it? Well, we use this term called conjugates. Okay? The conjugate simply means take the term that you have, in this case 1 plus the square root of 3, and write out the same thing except change the sign. So the conjugate of 1 plus or minus the square root of 3 is 1 plus the square root of 3. The conjugate of 5 minus the square root of 2 is 5 plus the square root of 2. You just change the sign. And we're going to multiply the top and bottom by that. And this works. This is still 1. 1 plus the square root of 3 over 1 plus the square root of 3 is still 1. And we're just going to have a little bit more involved multiplying here. 2 times 1 is 2. 2 times the square root of 3 is not square root of 6. It's 2 square roots of 3. Now, how do we multiply this down here? 1 minus the square root of 3 times 1 plus the square root of 3. You can FOIL it as well. You see it's a difference of squares problem. For some people, they're freaking out. I know there's hyperventilation going on right now watching this on your computer. But this is just 2 binomials. All we have to do, don't hyperventilate. Please don't do that. 1 times 1, make your box, do FOIL, whatever you want to do. 1 times 1, 1 times negative square root of 3, 1 times positive square root of 3, and negative square root of 3 times square root of 3 is minus the square root of 9. When I do this, I get 1 minus the square root of 3, I get square root of 3 minus the square root of 9. Square roots cancel out, that's nice. What is the square root of 9? That's 3. 1 minus 3 is negative 2. So I end up with a negative 2 in the denominator, which means I then can simplify. If I look, all of these terms can be divided by a 2. Actually, negative 2 in this case, to get the negative out of the bottom. 2 divided by negative 2 is negative 1. 2 divided by negative 2 is negative 1 square root of 3. So negative 1 minus the square root of 3 is simplified. Okay? That's a little more advanced using the idea of conjugates. Let's check and see if we did it correctly. This time, probably the easiest way is to use our fraction bar for both. 2 over 1 minus the square root of 3. That's our original. And we get negative 1 minus square root of 3. We did good. We got the same answer. Okay? So, that's simplifying radicals using conjugates. Okay, so let's check and make sure that we covered everything we're going to do. We said we're going to be able to simplify radical expressions. That's a pretty big, broad goal or target for the day. We saw there were several different ways we can do that. What did we do? We did it by using the product property. breaking things down using perfect squares, the quotient property, and then we also did rationalizing the denominator with and without conjugates. So bring your notes to class tomorrow. We're going to check those off. We'll do some practicing, and I'll see you in the morning or in the afternoon. Have a good evening.